So this week we're going to be discussing absolute threshold and differential sensitivity. So first let's talk about absolute threshold. As you know, absolute threshold is the minimum detectable level of sound for a listener. So how is that measured? Well, in psychoacoustics, there's two different ways that we can measure absolute threshold. The first one is to establish a person's threshold and then have a microphone that's inserted in their ear and placed near their tympanic membrane, and to measure the level of the sound by using that microphone. And that's called the MAP, or the minimal audible pressure. And since that's only inserted in one ear, then that's going to represent monaural listening, or listening to a sound just with one ear. Another way to do this is to establish a person's threshold by having them sit in a sound field and presenting the sound through a speaker. And then after their threshold is established, to put a microphone where that person's head was located and then measure the sound pressure level of the sound at that level. And that is called the minimum audible field. And that would represent binaural listening because it's in the sound field and we listen with two ears in the sound field. So here is a visual showing you the minimum audible field. That's the line down at the bottom. And then the minimum audible field measured at the tympanic membrane. And then the minimum audible pressure measured at the tympanic membrane. And what you can see in this graph is that the MAF at the TM and the MAP at the TM are very, very similar in their shape. And the MAF measured in the sound field is very different. And this is a result of the acoustics of the pinna and the head and the ear canal affecting the sound as it comes into the auditory system. Hopefully you've learned about this before, how the head and the pinna and the ear canal modify sound as it comes into the auditory system. So you can see a result of that here. Now let's talk about duration a little bit. And duration does have an effect on how we perceive sound. First of all, durations over 1 second are considered infinite. Really, once you go over 1 second, there's really no difference in your perception of the sound as it gets longer. But auditory sensitivity, however, is altered for shorter durations. Durations shorter than about 10 milliseconds result in transience. So there's really no tonality to the sound once it gets shorter than about 10 milliseconds. But looking at tonality itself, we go from a click to a click with a tonal quality to a tone. So we talked first about clicks, and that's shorter than about 10 milliseconds. Then frequency comes into play. Below 1000 hertz, a tonal pitch is heard when the duration includes several cycles of that 1000 hertz tone. Above 1000 hertz, threshold for tonality is about 10 milliseconds. So that's that golden 10 milliseconds that I talked about just a few seconds ago. Once you get above 1000 hertz, then you start to detect tonality when the duration of the stimulus is about 10 milliseconds or longer. Now I want to talk about something called temporal integration, and that's our ability to process a sound as it gets longer. So for durations up to about 200 to 300 milliseconds, a 10 times change in duration is offset by an intensity change of about 10 dB. And I have a graphic to show you on the next slide. So the ear is an energy detector, and it samples energy with let me try that again. The ear is an energy detector, and it samples energy within a certain time frame, approximately about 200 milliseconds. So there's a give and take here with duration and threshold for the tone. Additional energy past 200 milliseconds does not really contribute to the detection of a sound. And integration functions become flatter as frequency increases from 250 to 4,000 hertz. So here's the graphic I was talking about. And we have duration in milliseconds along the x-axis, and we have the intensity in dB along the y-axis. And what you can see is if we increase the duration by 10 times, then our threshold is decreased by 10 decibels. Or you could go backwards the opposite way. If we decrease our duration by 10 times, then we have to increase the intensity by 10 dB to perceive it at the same loudness. At durations greater than 250 to 500 milliseconds, the threshold in units of power does not change much, as you could see on the previous slide. Once you get to a certain point, and I can even back that up, once you get to about 200 milliseconds, you can see that the line's flat. So there's really no effect once you get to about that duration. At shorter durations, however, the power of a tone must be increased to reach threshold. And then for durations smaller than 10 milliseconds, much more power is needed to keep that threshold constant. So here's another way to look at it, just to help you picture it a little bit. If you think about how your ear just processes a block of energy. If you have greater intensity, as shown in this first block, then you can have less duration for the same area of a block. If you have greater duration, so it's drawn out more longitudinally here, for the same area you have less intensity, representing power. The area is representing power here. So there was a famous study that was done by Watson and Gingle in 1969, and they found the difference in duration perception using the method of adjustment, which we learned about a couple of weeks ago, versus a two-alternative forced choice procedure. And they looked at temporal integration for subjects with normal hearing and impaired hearing. And I have this paper attached to the last page of your interactive module, so you can look at that and read through it. And what they found were steeper integration functions for low frequencies and similar functions for both groups. So you can see this is figure 2, and figure 2 is looking at functions just for one hearing impaired and one normal listener. And both listeners show reduced integration as frequency is raised. So let me go through this just a little bit for you. You've got signal duration in milliseconds along your x-axis. And each panel here, the left and right panels, are separate. So you're going from 16 milliseconds to 1024 milliseconds in the first panel, and then the same thing in the second panel. And then you have the threshold shift with the reference being the average threshold along your y-axis. And then each line represents a different frequency. So what you can see is that reduced integration as the frequency is raised. So as you raise the frequency, there's not as much of a threshold shift. The top line there is 125 hertz, and then the bottom line there is, I believe, 4,000 hertz. I'm looking in the left panel. So you can see that there's not as much of a threshold shift because it's lower or more towards the bottom on the graph. Now this next one is this figure 3 that was referenced before. And this is looking at functions for the hearing impaired listeners on the left and the listeners with normal audiograms on the right. And we're only looking at 3 frequencies here. We're looking at 125, 1000, and 4000 hertz. And it's the same setup. We've got duration along the x-axis and the threshold shift referenced to the average threshold on the y-axis. And what you can see is there's a little bit of difference between the two, but there's not a huge difference looking at the equations here. Now this is figure 4 from the paper, and this is the average summation functions for 7 listeners, and each data point represents the average of at least 12 measurements for each listener. And so we're looking at this again. We have duration along the x-axis and the threshold in dB referenced to the average threshold on the y-axis. And again, what you can see, first you can see the function of the slope. 250 hertz is starting at the top, and it's a very sharp drop off as you look at the duration increasing of the stimulus. And then at the bottom we have 4000 hertz, and you can see that that function is not quite as steep. Also, what you can see is at very short durations you need a lot more energy, or there's a larger threshold shift at the lower frequencies as compared to the higher frequencies. So not only does duration have an effect, but duration interacts with frequency as we're looking at tones. So now we're looking at the difference between the two different procedures. We're looking at the method of adjustment, which is the bottom line, and then we're looking at the method of limits, which is at the top line, and then the two alternative force choice are the dark circles and the dark squares. So what you can see is that there is a difference depending upon which method was used. We have frequency along the x-axis and the difference in signal level along the y-axis on the left side, and milliseconds along the y-axis on the right side. And this upper solid line represents the data of Plomp and Baumann, which is a different study. And the lower solid line shows the 7 listeners of experiment 1. The solid symbols represent the force choice procedure, and the open symbols represent the same 2 listeners under the method of adjustment.